Okay, lesson 5.3, exponential functions. Today we are going to be graphing exponential functions. We're going to be exploring the different transformations of them, so that will occur right here. And we'll look at different examples with those transformations and how to apply the mapping notation. To start the lesson, let's go over some definitions and just a recap of what we would have learned in grade 11 about exponential functions. So, graphing the function f of x equals 2x. If we graph it on the axes on the right hand here, we need to get some x's and y's. So let's plug in the x's provided to us into our function. So calculate 2 to the power of -1. You would get 1/2. 2 to the power of 0, you're going to get 1. And then 2 plugging in 1. So again, like you're just taking these x's and plugging them into your formula. You're going to get 2. So plotting those on the curve, if I plot at a coordinate of -1, you're going to be at 1/2. So let's say that this is 1 right here. That would make 1/2 about here. And then at a coordinate of 0, you're at 1, so kind of already on the graph. And then at a coordinate of 1 on the x, you are at a value of 2. So let's say that's there. And that is what your graph will look like for f of x. This is f of x. And notice that I have arrows going on both sides of my graph. That's because I can keep plugging in numbers going negative and my graph will extend that direction. Likewise, I can go bigger x's and my graph will keep going up and up and up forever. So just so this lesson does not go on forever, all right, I'm not going to graph these right here, but I just want to go right into d of x. I want you to see the difference between having a base where you are bigger than 1 and then having a base here which is between 0 and 1, okay? How does that graph change? Well, same as we did before. You'd be taking a value, calculating your y's, taking your values of x and plugging it in here. So if you take 1/2 and you put it to the power of -1, you get 2. If you take any base, put it to the power of 0, you get 1. So then 1/2 to the 1 is 1/2. So let's plot that. Let's do it in green. So at coordinate of -1, you're at 2. So that was our 2 right up there. So you're right up here. At an x value of 0, you are right here. And at an x value of 1, you are at 1/2. So you're right here. So notice how the graph looks different. We're coming from the other direction because this one had a value that was between 0 and 1. Or another way to think about it is these are reflected. Look how d of x is a reflection. If you were to hold a mirror right up to this y-axis here, you can see that d of x is a reflection of f. Well, if we use our exponent laws, look, I can rewrite 1/2 as me saying 2 to the power of -1. And then if we use this multiplication here, of exponent laws, that's 2 to the -x. That is a transformation, that is a reflection over the y-axis. Okay? So if we look at these two graphs right here, let's explore some of the summary. Do they have an x-intercept? Is there a x-coordinate that you can plug in that would cause your function to ever be 0? If I take 1/2 and I plug in any number up here, will it ever equal 0? Or 2, if I plug any number up there, will it equal 0? And if you try it out for yourself, you would find that no, it's impossible. There's not going to be an x-intercept. And the reason for that is there is a horizontal asymptote at y equals 0. And how do I know that? How do I know that at y equals 0, there's a horizontal asymptote? Well, for one, this way, right? Any number, I know that I'll never get an output of 0, meaning that these functions will never hit 0. Or we can also just look at transformations. As we'll see later in the lesson, the c value, the thing that's on the backside, if you have no number here, technically this is like me saying plus 0. But whatever number this is, that's going to be your horizontal asymptote. So if I go down for a second, I'm going to jump ahead in the lesson. This right here, this plus c, all right? So in this first example, it's minus 4. That will be your horizontal asymptote, whatever number is on the backside. So because I don't see any numbers here, because this is technically plus 0 here, right? Even on the 1/2, this is like me saying plus 0. That means both of those have a horizontal asymptote at y equals 0. The y-intercept was 0, 1 in both cases. That's because any base, I don't care what number it is, being put to the power of 0 will always give you an output of 1. That's why it didn't matter if it was a fraction or a whole number. The output was 1. And then inside of exponential, a characteristic of exponential functions is that you do not have a vertical asymptote, meaning that there is no value for x that will cause this function to be undefined, okay? That's what a vertical asymptote is. So there is nothing that will cause this to be undefined. End behavior. So when we look at end behavior, as a recap from Unit 2 and Unit 1, we are looking at the left of the graph, and we are looking at the right of the, vice versa, right of the graph for the positive infinity and left of the graph. And how are our two functions behaving? So let's look at f of x. All right, that was the 2 to the x graph. What was happening? As we went towards, oh, sorry, that one was done in purple. Let's keep it the same. So as we looked at f of x, we can see that as you go to the right of the graph, you are going up forever. So as we move towards positive infinity on our x, we're going up. So as x goes to positive infinity, f of x also goes to positive infinity. But d of x, well, this function, as you move towards the right, you can see we're getting smaller and smaller and smaller. You might say negative infinity, but if you do say that, well, we'd be wrong, because the problem is you can't go to negative infinity. Like, you cannot hit a value smaller than your horizontal asymptote. This graph will approach 0. You can see that. As we go towards positive infinity, you're going to be approaching your horizontal asymptote, your y equals 0 horizontal asymptote. If we do the same for looking on the other side of the graph, f of x, well, as we look on the left side, we can see that we are approaching the horizontal asymptote. So that's going to 0. And d of x, this one was going towards positive infinity. We can see that d of x, as we look to the left of our graph, this was going up forever. Well, a characteristic of exponential functions is that the domain has no restrictions. There's no restrictions on the x. Okay? It's because we have no vertical asymptote. The range, well, it's y belongs to real numbers. And in this case, both functions had to be bigger than your horizontal asymptote, right? So they both had to be bigger than 0. So when the base is greater than 1, all right, your function looks like this. And you would say this function is increasing. When the base is between 0 and 1, your function will look like this. I should draw arrows on both sides of the graph. And you'd say that this is decreasing. Okay. Now, we're not going to be always graphing exponential functions that are of the form b to the x, right? As we saw with the 2 to the x and the 1/2 to the x. It's going to get more complicated, where we have these different transformations that occur. But these transformations are identical to everything we have done in the past, okay? It doesn't matter what type of function you're looking at. The value here, this multiplication in front, this a, is identical to what we did in quadratics, what we did in trigonometry, okay? It's the same. That a will cause a vertical stretch or compression by a factor of a, whatever it is. If it's 2, it's a stretch of 2. And so let's say that. So if the value of a is bigger than 1, that's a stretch. If the value of a, like let's say it's like 1/3, that would be a compression. So if it's between 0 and 1. But there's two parts to a, right? Notice how I'm putting these magnitude signs. Well, the second part to a says that if the value of a is less than 0, right, meaning it's negative, i.e. negative, well, that's going to be a reflection over the x-axis. Okay? The k value. So this part, right in here. And notice how the k value is always factored out, okay? So always be on the lookout for that. Well, the k value, as we've seen in other functions, that has to do with horizontal stretching and compressing. So your horizontal, I'm going to give myself some room so it's very clear which one I'm writing. Okay. So the k has to deal with horizontal stretch, right? And this happens, it's stretching when you see the value of k, I should say the magnitude of k, is like a fraction, or compression, when the value of k, the magnitude of k, is bigger than 1, right? So it's opposite of a, right? So you have a horizontal stretch compression by a factor of, and this is the part that always throws people off, 1 over k, right? So if you saw, I mean, we'll see it in later examples, but like let's say you saw some base put to the power of 2x, right? That 2 would cause this to be a compression by factor of 1 over 2, okay? And then similar to the a, and we saw when we did the 1/2, the k has a second part to it, all right? If the k value of k is less than 0, so again, talking about being negative, there will be a reflection over the y-axis. And we saw that with the example above. So your d, the d right up here, the one that's inside the bracket, all right? That's like, think of it as attached to the x. That's your horizontal shift left and right. That's your horizontal shift, left, right, by d units. D units. And then the last one, we have the C value, which is your vertical shift up/down by C units. But also, as I've told you, the C value is your horizontal asymptote. This is your horizontal asymptote, whatever it is, right? Whatever number you see. If you don't see a number, that's because you have a horizontal asymptote at 0. So let's do an example. Graph the function f of x equals 3 times 2 to the x minus 4. Well, the transformations, we have to talk about this 3 that we see in front, and we have to talk about this minus 4. So the 3 in front, that's going to be a vertical stretch by a factor of 3. And the 4, you know what, just you see where on your notes, I'm going to underline the green and then write in green. That 4, that will be a vertical shift down 4 units. Okay. So we're going to graph it, but because I see that there is a minus 4 here on the backside, right off the bat, I can put a horizontal asymptote at y equals 0, at y equals -4, sorry. I know that will be there. All right, but let's get another picture of the graph. So in order to draw this graph, we're going to be using mapping notation. So in order to do mapping notation, we need to know points from our parent function. So let's get some x's and y coordinates from our parent function. But what is the parent function? The parent function it's the function that has no transformations. So we've stated our 2 transformations. So if I look at this and I get rid of our transformations, we can see that your parent function, the one that has nothing to it, would be f of x equals 2x. So our transformation is y equals 2x. That's your parent, sorry, not our transformation. Our parent function is y equals 2x. Our transformation is us taking these x's and these y coordinates and applying whatever transformations occur according to this right here, okay? So in our case, we have no k value and we have no d, so all of your x coordinates are going to be the same. But we have an a value and we have a c value. So you're going to take your y coordinates and you're going to multiply them by the a, so 3, and you're going to subtract, in this case, 4, because that's your c value. But what x's and what y's do I put in here? Well, that comes from the parent function. So choose values for x. X is your independent variable. Choose them. Anyone's work. So just so this video to the lesson does not go on forever, I'm just going to choose 3. But on an assessment, try to choose at least 5. That way it gives you a better picture of your graph, okay? But for the lesson, I'm just going to plug in 3, all right? So I'm evaluating my y coordinates when I plug in those x's for that x right there. So if I plug in -1 for 2, I'll get 1/2. If I plug in 0 up top, you're going to get 1. And then if I plug in 1 up top, I will get a value of 2. So as I said, your x's are the same. So these are still -1, 0, and 1. I'm just taking exactly what I see here. These ones are going to get transformed. So your new y coordinate happens when I take 3 and I multiply my previous y, which was 1/2, and then I subtract 4. So doing that, well, we got fractions, so that's like me saying 3/2, take away 4, which is the same as -2.5. So your new coordinate you're plotting is an x of -1 and a y of -2.5. Let's do the same for 0. So it's 3 multiplying 1, sorry. All right, because I'm pulling this right here. Subtracting 4. So that's going to give us -1. And then I have 3 multiplying, what was our other y coordinate? 2. So 2. Subtract 4. That's going to give you a value of 2. So we've created one ordered pair. Our second ordered pair was the x of 0, 0, and -1. And then your third pair was x coordinate of 1 and 2. So you're plotting those points. You're plotting these 3 coordinates here. And that would be your transformations. All right, that's your function has been transformed by just doing that. So we need the coordinate -1 on the x. So -1 on the x. And we're going to be at -2.5. So if that's -4, let's say -2.5 is right about here. So your coordinate would be right there, your point side. 0 and -1, so 0 on the x, -1 on the y. So let's say that's -1. So there's your second point. And then 1 on the x and 2 on the y. So 1 and let's say that's 2. So your point will be right about there. So connect your dots. There you go. And then we know we're going to be coming down towards our horizontal asymptote and leveling off like that. And this function is f of x. Okay. Identify the features. Well, our horizontal asymptote, that was your c value. So in this case, that was y being -4. The y-intercept, well, we so happen to have found it by just using our mapping notation. That was 0, -1. But let's say you weren't lucky and that wasn't one of the points you calculated using your parent. You can calculate it by just substituting in 0 for your x into your original function. So I would plug in 0 into my function being 3 times 2x. So now I'm subbing in 0, -4. So that's 3, 1, -4, or -1. So yes, algebraically, we got the same y-intercept. Is the function decreasing or increasing or decreasing? Well, let's look. Left to right, you can see that the function is getting larger. So this function is increasing. I don't care what the function looks like. I can just right off tell you this because a characteristic of exponential is domain is anything. It could be any number. There's no restriction. The range in this case is y belonging to real number. And I look and I see that I am above my horizontal asymptote. So my y's are always above that -4 coordinate. Okay, so I'm just going to move past this question. Try it for yourself. My solution is posted. But just for the sake of time, I'm going to move on to the next question. All right, this one is a little trickier, and that's why I want to do this one. So we're graphing f of x, which has the base 4 being put to the power 0.5, x minus 2, and then subtracting 1. So let's state the transformations. But this one's a little tricky because up top here, we now have this k value. But notice how you don't see any brackets here, all right? Always remember that if you have a k value here, you should see brackets. So I can't just put brackets like that and call it a day. You have to first factor out the k. So that means this function is actually 4 being put to the power of the k value, 0.5. But when I factor it out of that binomial up top there, well, -2 being divided by 0.5 means that this becomes -4. So if you didn't factor it out, you would have told me that there was a shift of -2, but that's not the case. There's actually a horizontal shift of -4. And we still have that -1. Okay, so now state the transformations. Well, this k right here being 0.5 is going to cause our function to have a horizontal compression, or sorry, stretch, by a factor of 1 over 0.5, so 2. You have that shift, that horizontal shift, and because you see -4 there, you know that you're going to be going to the right, so the right 4 units. And then that -1 on the backside there, that's going to be a vertical shift. Vertical shift down 1 unit. Okay, so we're going to be using our parent function, our points from our parent function, transforming them to graph it. But before I even do that, I'm going to just plot the horizontal asymptote. I see a -1 on the backside, so we have a horizontal asymptote at y equals -1. That's always the case, okay? So just make your life easy and start there. So let's get our parent function. So you need to ask yourself, what is the parent function, the base exponent that has no transformations on it? So if I was to get rid of that 0.5, that -4, -1, what you'd be left with is just 4 to the x. So let's get points on our parent function, -1, 0, and 1. So again, I'm just choosing 3 points. I don't want this lesson video to go on forever, but if you need more points to get a better picture of the graph, please use more. All right, let's get the y coordinates. When x is -1, that would cause this function to be a y of 1/4. When you're at 0, you are at 1. And when you are an x coordinate of 1, you are at 4. So let's transform those points. So all of our x coordinates are going to be being divided by the k value of 0.5. And then because we're moving to the right, we're going to be adding 4. And then your y, so we didn't have an a, but we had a c. So all your y coordinates are going to be subtracted by 1. So take this x of -1 and plug it in here and calculate what you get. So that's -1 over, I'm going to do it a little bit aside, -1 over 0.5 plus 4. So how many times does 0.5 or half go into -1? Well, twice. So that would be -2 plus 4. So that would give you a coordinate of 2. And then 1/4 take away 1. So 1/4 take away 1. It's going to be -3/4. So there's your first coordinate. I'll just draw a line so we don't get confused. And then 0 being divided by 0.5 plus 4. That is just 4. And then 1 take away 1. Well, that's a 0. So there's your next 2 points. Or that's your next ordered pair. And then plugging in 1, dividing that by 0.5, adding 4. So that's going to be 6. And then 4, take away 1, that is going to be 3. So we're plotting the coordinate 2 and -3/4. So let's just put that as a decimal though. So -7.5. We're going to be plotting 4, 0, and then we're going to be plotting 6, 3. So let's put those on the graph at 2 and -0.75. So 2, our x, our other one is going to be 4, and our other x is going to be 6. So I'll just put those there just so we can see. So that's, sorry, I shouldn't do circles because it's going to make you think those are points. 2, 4, and 6 on the x. Okay, so at 2, we're at -7.5. So that would probably be right about here, I would say. It's really close to that. It's really close to that asymptote. At 4, you're at 0. So right there. And at 6, you're at 3. So let's say 3 is all the way up here. So there's your function. Connect your points. So that's going to go up forever. And then this is going to approach your asymptote like this. And that was f of x. So key features. Well, our horizontal asymptote, that's a c value. That is y being -1. The y-intercept, well, in this case, I didn't actually get one from our table of values, so I will need to algebraically calculate it. So that occurs when x is 0. So if we look at our function, which is 4 being put to 0.5, x minus 4 minus 1, evaluate it at the coordinate of 0. So that's 4, 0.5, 0, take away 4, minus 1. So that's 4 to the, well, this is -4, times that by 0.5. It's going to be minus 2 up top. So that will be 1 over 16, take away 1, which would be the same as me saying -15/16. So your y-intercept is at 0, -15/16. Is the function increasing or decreasing? Well, let's look. We are going up as we read left to right. So this is an increasing function. The domain, x belongs to real numbers, and the range is y belongs to real numbers, such that you have to be greater than our asymptote, which was at -1. Okay, and that's the lesson. Bye for now.